In both parts of lecture 14 for differential equations and linear algebra, we're going to more live up to our alternative name for the course, continuous and discrete dynamical systems, systems that change over time in a continuous or discrete way. Lecture 14a, as usual, is about differential equations. We'll see how the dynamical systems comes up there, especially with this idea of a vector field, this is going to be the first lecture where we talk about that important idea. In lecture 14b, that's about linear algebra, but we're going to be talking about linear difference equations and how when you iterate a linear transformation, some pretty interesting things can happen. This is getting into my favorite part of the course, and we're also starting to see how these subjects mesh together, so watch for that. So let's start by reviewing the undamped simple harmonic oscillator. I talked about this in lecture 13a. This is a review of that. The simplest kind of simple harmonic oscillator is a mass and a spring. There are other kinds of simple harmonic oscillators, for example, in electric circuits. But it's sort of simplest for most people to think about a mass and a spring. So you've got a block of wood, say, attached to a spring attached to the wall. You try to minimize the friction here initially as much as possible. So maybe this is ice down here and there's a vacuum. But of course, you can't completely get rid of the friction from the spring itself. All you can really hope for is that the friction is minimized so that the undamped model is a decent approximation to the motion of the mass, back and forth. The block has mass m in kilograms. The spring, that red thing that you see here that can go back and forth, has spring constant k, also called the stiffness constant, in newtons per meter. The stiffer the spring is, the greater the restoring force is. That means the bigger k is. And then some unstiff kind of spring, like a slinky or something, would have a small value of k. Y is going to be the displacement or position of the block from its equilibrium in meters. You can imagine maybe in this picture that the y-axis is horizontal here and say positive to the right, and pretend the mass is at rest right there. Put y equals 0 at the center of mass of that block of wood. Again, in the undamped case, we assume no friction is present. Laugh out loud, that's not realistic, but we hope it's good enough. Hooke's law is that the restoring force of the spring is proportional to the displacement y with a negative constant in proportionality. I talked about that in lecture 13a and why that made sense. I will re-emphasize that this is just an approximation. It's not necessarily a perfect model, but it really is the simplest model, and that's why we like it. Newton's second law says F equals ma. A, the acceleration of the block of wood back and forth, is the second derivative of the position with respect to time. You combine these two things and you get a second order linear and homogeneous ODE. Ma, that's mass times acceleration, equals the force, the restoring force due to Hooke's law, negative ky. You can divide both sides by m and write it this way. You can add k over my to both sides and write it this way. And it's in this manner that you emphasize that this is a linear function, linear operator on the function y, and the right-hand side is 0 so that it's a homogeneous ODE. Oftentimes we will let q equal k over m to make the equation a little simpler, okay? So now we want to look at some solutions to this. And we want to note that the general solution in this case, well, it can be found by guessing, but you need to realize that after you've found it by guessing some cosines and sines, you really have a linear combination of two particular solutions to that ODE, cosine of square root of k over m times t and sine of square root of k over m times t. We've talked about linear combinations before in the linear algebra lectures, the part B's. There we were doing linear combinations of vectors. Now we're doing linear combinations of functions. This is all to set us up to the point where in the next lecture or two we can talk about function spaces in more depth and also talk about the abstract idea of vector spaces. Really important to see how the abstract idea applies to particular kinds of examples. It is a linear combination. I'm going to keep emphasizing that. And in fact, you can even say a little bit more related to linear algebra. You can even say the so-called solution space of that differential equation is the set of all linear combinations like this where A and B can be anything. You could call that the span of that cosine function and that sine function. Cosine square root of k over m times t, sine square root of k over m times t. I'm running out of room here. Let me put this down. Further sine of square root of k over m times t. Remember that the span of a collection of vectors I did mention is the set of all linear combinations of those vectors. But you might be scratching your head and saying, well, these aren't vectors, they're functions. Well, in the more abstract setting of a vector space, we are going to consider functions to be vectors, examples of vectors. And this span, called the solution space for that differential equation, will actually be something called a vector space. And it will be two-dimensional. These two functions will span the space, and they will also be what we call linearly independent, a very important idea to come. Turns out we need two initial conditions to be able to solve for A and B. I hope that makes some intuitive sense. You need the initial position, and you also need the initial velocity. Call the initial position y sub 0 or y naught. It needs to equal y of 0. Call the initial velocity v sub 0 or v naught, if you prefer. That needs to be the derivative of y at 0. So that allows you to solve for A and B. Now, I'm not going to do an example. We will do more examples to come, but we've got a lot to get through here. What's the corresponding first-order system? The original differential equation was a second-order differential equation. I can convert that single scalar second-order equation to a first-order system involving just first derivatives. What's the benefit of that? Well, it is easier to interpret geometrically, we will see. And we will also see that it's easier to apply Euler's method to a numerical approximation scheme when we need to. You start this by defining v to be the derivative of y with respect to t. V is the velocity, which again, as usual, can be positive or negative, just as y can be positive or negative. Y is positive if you're to the right of the equilibrium position and negative if you're to the left. V is positive if the motion is toward the right, no matter where you are, positive velocity. V is negative if the motion is toward the left, no matter where you are. Okay? This corresponding system has a first equation given by this definition, dy dt equals v, and a second equation, dv dt equals negative k over m times y. Why? Pun intended. Because dv dt is the second derivative of y with respect to t, and we saw from the previous slide that that equaled negative k over m times y from Newton's second law and Hooke's law. That's where this first order system comes in. And again, it's first order because it only involves first derivatives. It's a system. We think of these as a combination of differential equations that are interacting with each other. And we can write it in vector form with vectors and matrices. I'm calling it matrix slash vector form. If we define it vector capital Y, I'm going to use capital boldface Y in the differential equations portions of these lectures because that corresponds to our Blanchard, Devaney, Hall textbook. In the part B, linear algebra, I'm going to, at least today in this lecture, use the letter boldface X, and actually it won't be capital, it'll be lowercase boldface X. Don't let that bother you. It's not a big deal. It doesn't matter what we call these things. The components of capital Y are little y and little v, not little x and little y. I want to relate it to the mass of the spring. Its horizontal position, which I am calling y, I could have called it x, and its horizontal velocity. That's going to be very, very important to keep track of that. Notice these are not going in alphabetical order. The derivative of that with respect to t, by definition essentially, has a first component of dy dt and a second component of dv dt. These things do depend on t. I am thinking about the motion of the mass on the spring over time. It's oscillating back and forth. It's got a sinusoidal kind of position. You can graph it. It's going to look like a sine wave, possibly with some unspecified amplitude that you might have to figure out, some period you might have to figure out, and perhaps some phase angle that it's called, some horizontal shift that you might have to figure out. These things depend on time. I'm assuming in a differentiable way. I'm assuming I can find these derivatives. Then we can write the differential equation in this vector form as dy dt equals this vector equals this vector. Why? Because it's essentially just combining these two scalar equations into one vector equation. dy dt equals v, so these first components are equal. dv dt equals negative k over m times y, so these second components are equal. But that, if you're careful, is a linear combination, there's that term again, linear combination, of two vectors in the usual sense. This was a linear combination of functions. This is a linear combination of two fixed vectors, where the weights, the coefficients, are little y and little b. And the reason I did that is to emphasize again that that's the same as a matrix times a vector. Oops. This matrix times this vector. Why? Because of how we defined matrix vector multiplication. And it's very good to remind yourself of that. When you take this matrix times this vector, you form a linear combination of the columns of the matrix with the components of the vector as the corresponding weights. So we get y times this first column, which is what you see there, and v times this second column, 1, 0, which is what you see there. Okay? I'm going backwards. I'm saying I'm going from the linear combination to the matrix times the vector. Usually we go the other way, but it's still true. And I can call this matrix, say, capital A, and this vector is the same as boldface y, so I can write the differential equation ultimately as dy dt equals a times y. And that's a beautiful thing, and it's going to connect to the scalar form dy dt equals a times y, which we know has general solution, an arbitrary constant times e to the at. That's the scalar case that we already knew about from way back in lecture 1 even, I think. Certainly lecture 2. That's going to connect now to this vector form, and we will eventually see that E still becomes involved in something called the matrix exponential. These are all really cool things. All right, continuing. What's a vector form of the general solution? Go back to the scalar form. This is y as a function of t. That's the position. That's what you really care about most. The position of the mass is a function of t. But if we want to think of it in terms of the matrix vector equation, it's good to find the velocity. It's good to differentiate that to get this. And then you can put this in the vector, capital Y, boldface. Like that, right there. And then if you want, you can separate this out into a linear combination. There it is again. Of these two vectors with capital A and capital B as the weights. And I guess that also means we could think of it as a matrix multiplication here, but I didn't. You could think of it that way, but I avoided doing that at the moment. It's a parametric curve. These are vector-valued functions. Give me a real number t. These two things give you vectors as output, which we typically draw as parametric curves, and which I'm about to show you for a particular example here. If we take m to be 1 kilogram and k to be 1 Newton per meter, and let's also just pick something specific for a and b, take a to be 1 and b to be 0, then the solution is this parametric curve, okay, which we will also graph in the yv plane. Notice I also could graph, say, just the first component in an ordinary kind of graph. Say with t as the horizontal axis and y as the vertical axis, graph the cosine function, you know, it looks about like this. And it goes on forever and ever. That's representing the horizontal position of the mass. Don't be bothered by the fact that y is vertical here, whereas in the mass picture, y was horizontal. We're starting at 1 meter from rest at t equals 0. This is 1 right there. And we're letting it go from the rest because the derivative right there is 0. The instantaneous rate of change right there is 0. It's let go from rest. V, the velocity, is 0 when t equals 0. And you could graph the velocity in here as well, though you'd want to label the axes with a v as well. It would be the negative sine function, which I'll just do it with my finger, would look about like this. Okay? And that would be the velocity. But we want to graph it in this phase plane. Now, what is a phase plane? I've talked about it before. It's the, in this case, plane of y and v, your dependent variables for your system of differential equations. And for a given initial condition, a given initial position and initial velocity, you need both. You're going to get a solution curve starting at that point at t equals 0. In this case, the solution curve comes back to where it starts. Our initial position based on this at t equals 0 would be at this point right there. That's when the mass is pulled 1 meter from its rest position and let go. At that instant in time, the coordinates y comma v of this point, y comma v, which would be 1, 0, tell you the initial state of the system at time 0. The mass is 1 meter to the right of the rest position, and that instant it's being let go, it's got a velocity of 0. The arrow goes clockwise here. As time continues to go by, we move along this curve in the phase plane, meaning the position and velocity of the mass and the spring are changing over time. When we happen to be, say, right about here, the position is pretty close to 0.025 or so, and the velocity is close to -1. The mass is moving to the left, its velocity is negative, and it's just to the right of the equilibrium position. When it touches right there, that's when it's at equilibrium. Y is 0 there, and V is -1. The velocity is most negative at that moment in time, which, by what I picked here, would be t equals pi/2 seconds. That's when that would happen. Pi/2 would be about 1.57 seconds or so. It's actually a fairly slow-moving block of wood. But it comes back to where it started. It's a periodic solution. The phase plane emphasizes the state of the system. Here's an animation reminding you that you should really think about the solution as moving through the phase plane. Ignore the backwards motion. Okay, that's just an artifact that when I make this into a GIF file, it goes backwards. Focus on the forward motion as it's going clockwise, like starting now, and going around twice. The black dot is the state of the system at the given moment in time. I drew some arrows in here, some vectors, because it's going to be helpful. The red vector, based at the origin, with its tail at the origin, and its head, its tip, at the black dot, is called the position vector of the black dot. It's a position vector for the system, you might say. The pink vector is the velocity vector for that red vector. It's somehow its rate of change, and notice it's always tangent to the curve. Is it the same as the velocity of the mass on a spring? No. The velocity of the mass on a spring is a scalar quantity that can be positive or negative. Again, positive for motion to the right, negative for motion to the left. This pink vector is not a scalar quantity. It's a two-dimensional vector. It's got an extra degree of freedom, you might say. It's related to the velocity of the mass. Okay? The velocity of the mass for the black dot is the second coordinate of that black dot over time. It's related to that, but it doesn't equal it. It's the velocity vector for the curve itself, if we're thinking of the curve itself as describing a motion, which we certainly can do. And that's a useful way to think about it, as I will show you here. Why does the parametric curve solve the system when m and k are 1? As always, as I've always been emphasizing, we need to check for the differential equation that the left-hand side equals the right-hand side upon substitution of the proposed solution. What is our proposed solution? Well, what's the system in this case, first of all? I picked m and k to be 1, so negative k over m is -1. Negative k over m is -1 over 1 is -1. That's what goes there in the lower left corner of the matrix. This is the matrix for our system. So it's our capital A matrix. Our proposed solution is this parametric curve. Y equals cosine, little y equals cosine of t, little v equals negative sine t. What's the left-hand side become when you simplify, when you substitute? You need to differentiate this vector. By the way, I certainly could have written an of t in here. I just didn't bother. I could have done that on previous slides as well. Differentiate component by component. The derivative of cosine of t is negative sine of t. The derivative of negative sine of t is negative cosine of t. Okay, that's what the left-hand side of the differential equation simplifies to. What about the right-hand side? A times y. Take the matrix A and multiply it by your proposed solution. We can think of it as linear combinations of the columns, but we don't have to. Remember, we can think of it in terms of dot products as well. That's going to come in handy, especially in lecture 14b, to remember that. 2 by 2 matrix times a 2 by 1 matrix, or vector, is a 2 by 1 matrix, or vector. The first component is the dot product of the first row of the matrix on the left and the first column of the matrix on the right. 0 times cosine plus 1 times negative sine of t is negative sine of t. The second component is the dot product of the second row of the matrix on the left dotted with the first column of the matrix on the right. Negative 1 times cosine of t plus 0 times negative sine t is negative cosine t. That's the left-hand side. Oops, that's a... Oh yeah, this is the right-hand side. Simplifies to this. That equals the left-hand side. It equals this. For all t, remember our upside down A means for all t, we're done, yay, check. It does solve the system. Now we're thinking of it not in terms of two scalar equations to check, but one vector equation to check, but they're equivalent to each other. As we saw in the previous slide, we know that we can geometrically interpret this solution function, this parametric curve, as a vector in terms of the position vector of the corresponding point. Here I'm writing it as a point. We want to be flexible and be able to go back and forth between vectors or points and their position vectors. Don't let that bother you. Here's something really important. We want to understand, why does the solution behave the way it does in that phase plane? The derivative, dy dt, which is negative sine of t, negative cosine t, can therefore be interpreted as the velocity vector of the same point, that pink vector. Because dy dt, the derivative of this parametric curve, will be its velocity vector. That changes over time. And it's best to draw it with its tail at the black dot, at the location of the point as it moves. The differential equation is really saying that at any given value of t, this velocity vector at the given point is equal to the vector quantity a times y equals v negative y at that same point. Now that might seem confusing, okay, but it's really important to get. I'll try to redraw the same parametric curve, or part of it at least, in this yv plane, y horizontal, v vertical. Say we're at a moment in time where the dot happens to be right there. The velocity vector for the curve at this point will look about like this. It's going to be tangent to the curve. In fact, that's what I say here next. When it's non-zero, when the vector is non-zero, it's tangent to the curve. It's pointing in the direction of motion at that given moment in time. And it's got a length equal to the instantaneous speed. Again, not of the mass of the spring, not of the mass of the spring, but the point as it moves around the plane, pretending this is an actual physical plane. Maybe you even use ordinary kinds of units for the axes, y in meters and v in meters or centimeters, whatever. The length of that vector is telling you the speed of this point at that moment in time. I don't know if you remember, but in the animation, the pink vector had a constant length. It did change direction, but it had a constant length. The point moved around the circle at constant speed. At that given point, if you find the vector v negative y, it will be this exact same vector. Now, let's just pretend we've got coordinates for this point. Well, let's go ahead and use exact coordinates. Say negative 1/2, negative square root of 3 over 2 is the point, yv. That means this vector has components v negative y. Switch these things around and put a negative sign in front of the second one, in this case making it positive. So we'll get negative square root of 3 over 2, positive 1/2 is what that vector is. The horizontal displacement is negative square root of 3 over 2, and the vertical displacement is positive 1/2. I didn't draw it perfectly, those look like they're the same length, okay? That's just because I didn't draw it very well, based on where I was. The solution curve seems to be following some tangents, just like solutions in the scalar case follow tangents for slope fields. Is there an analog of a slope field that the solution curve is following here? Yes, it's called a vector field. This is something new. first time I've really talked about vector fields in this class. What is a vector field, in the plane at least? It's a function. It's a function that we conceptualize in a certain way. We think of it as assigning or attaching a vector to each point in the plane. Kind of like there's an arrow attached to this point. It's that one, that vector. To be a little bit more precise, it's a function from the plane to itself. Using a boldface f here. This should feel a little familiar. Isn't this the kind of notation we use for linear transformations? Yes, it is, except we don't boldface them. In general, we think of the formula in this form. F of xy, boldface f of xy, there we go. Bold-faced f of xy is a vector whose components are little f of xy and little g of xy. Notice I'm writing that as a point for the input. And I'm writing this as a column vector. I'll just say vector for the output. That's because of the way we visualize it, conceptualize it. Taking points for input and giving you arrows, vectors for output. It's not that I have to write this as a point, it's just helpful because it's the way I'm conceptualizing it. In our example, where we had a matrix capital A that defined the vector field, A times Y defined the vector field. In fact, this function is linear. It's even a linear transformation, you could call it. However, we do not visualize it as a mapping, as we have been talking about in our lecture Bs with linear transformations, starting with the very first time we talked about them as official linear transformations. We talked about rotations and reflections and dilations a little bit. That's coming back in today's lecture B, 14b. And we'll think about it as a mapping for 14b, but here in 14a, it's not a mapping. We're thinking of it as a vector field that we draw like this, for example. And I couldn't get Mathematica, which I used to make this plot, to draw the output here as a column vector. But what I really mean in this label here is this is the column vector v negative y, because it just wasn't letting me put that in the plot label. This is the vector field that I'm drawing for this right-hand side function for this system of differential equations, which again is 0, 1, negative 1, 0. That's the matrix A times YV. How is it drawn? Give me any point. Plot this arrow at that point. At the origin, y comma v equals 0 comma 0, I get a vector whose components are 0, 0, which we always visualize as a dot. Put a big dot at the origin. That's going to be an equilibrium point for the system of differential equations. In this phase plane, an equilibrium solution. It stays there for all time. I haven't drawn solutions, I've drawn a bunch of arrows. Take this particular arrow right here, based at this point right there. That point has coordinates y equals, yv equals 1, 2. Y is the first coordinate, v is the second coordinate. The arrow for that point is right here. It's a vector, an arrow whose components are v negative y. V negative y, if v is 2, this becomes a 2 here, and if y is 1, this becomes a negative 1 down there. That's an arrow whose horizontal displacement is positive 2, and whose vertical displacement is negative 1. 2, 1. 2 I hat minus j hat, if you prefer. That's what it looks like at that point. Now do it at every other point, or at least lots of them, so you get a nice picture like this. Isn't that a pretty picture? Oh boy, that picture, oh boy, yeah, I just can't resist calling this some sort of rotation. Some sort of flow around the sink. Maybe the origin is like a sink, and the water goes down the sink. or maybe not, maybe not, maybe it just keeps going around and around without going down the sink. In fact, we know it doesn't go down the sink. We know that solutions are periodic. Solutions do have to follow this. Solution curves must follow or obey this vector field in the phase plane. Why? By what I said previously. Because the velocity vector for solution curves need to match the vectors on the right-hand side of the system. This was equal to d capital Y vector dt. That's the velocity vector for a solution curve. It's got to equal the output of the vector field at any given point you happen to be at any given moment in time. The blue curved arrows that you see in this picture are supposed to be solution curves, just not animated. They're supposed to be solution curves. They're all circles centered at the origin, going clockwise. They all represent certain motions of the mass in the spring that are all periodic. With no friction, the mass always comes back to where it starts, and then the cycle repeats itself over and over and over again, forever, with no friction. And yeah, these green arrows, when they happen to touch one of the blue circles at their tails, like, for example, this one here is pretty close. It's tangent to the curve at that point, pointing in the direction of motion, has a length equal to the speed of the point on that parametric curve at that given moment in time. And for any given circle here of a constant radius at the origin, those green arrows actually have a constant length because it's constant or uniform speed motion for the parametric curve around the circle. Although the arrows get longer as you move away from the origin, solutions that start out further away move faster to make the period the same no matter what the initial conditions are. The period of this motion, which you may want to figure out in terms of K and M, is constant as long as you're not at the origin. And that does imply solutions that are further away need to move faster so they can make it around one circuit of the circle in the same amount of time. The circumference of those circles is bigger. Take a breath. Getting close to being finished with lecture A here. More really important stuff. Okay, all this is super important for differential equations, and we are relating it to linear algebra here. In general, now I'm about to talk about what are called Nullclines. In general, the two sets of points defined by where each of the two components of the vector field are zero are very important for understanding the vector field and the corresponding solutions in the phase plane. In general, for a vector field, boldface f of xy equals first component little f of xy, second component little g of xy. In general, our variable names might be x and y here. For our example, they are y and v. The set of points where its first component is zero is going to be called the x nullcline. X is the first variable. It's defined to be this set. The set, the collection of all points in the plane where f of xy is zero, where this first component is zero. On the other hand, the set of points where the second component is zero is called the y nullcline. These things are zero. Nullcline kind of means zero curve. Null means zero. Cline kind of means curved line. Nullclines. Isn't that a great word? It's defined to be the set of all points where the second component, g of xy, equals zero. Since dx dt equals little f of xy, we're talking about scalar equations now here instead of vector equations, and dy dt equals little g of xy. Non-equilibrium solution curves cross x nullclines with zero first component, zero horizontal component. In other words, the tangent to the curve when it crosses an x nullcline has to be vertical. The motion has to cross an x nullcline with an upward velocity vector at that moment in time or a downward And the y nullcline with 0 second or vertical component yeah, they have to cross the y nullcline horizontally is what that means. The vertical component of the velocity vector of the solution curve is 0. It's got to point to the right or to the left. You have to cross y nullclines that way. For our example, the undamped harmonic oscillator, again, be careful about variable names. I'm using y and v instead of x and y. There's what the vector field and solution curves look like in this phase plane. What's the y nullcline, which is where the first component dy dt equals 0? The little f of yv is v, right? Because our system, the vector field was v negative y, right? That was 0, 1, negative 1, 0 times yv. The little f of yv equals v. And the little g of yv equals negative y. F equals 0, v equals 0. In this picture, that's the horizontal axis. That's where v equals 0. That's the y nullcline, which is the first component nullcline here. Solution curves are crossing it vertically. Any green arrow based on the y-axis either points straight downward, like the ones over here, or straight upwards, like the ones over here. Like this one, for example, right there, that goes up like that. And the other nullcline, the v nullcline, the second nullcline, is where g of yv equals 0. In other words, where y equals 0, which in this picture is the vertical axis. And you can see solution curves are crossing that horizontally, to the right up here, and to the left down there. Okay, that's our example of a nullcline. We're going to use nullclines a lot, and they really help you understand what's going on with the vector field and then with the solution curves as well. One more slide, I think. I think this is the last one. Note that the equilibrium point, which was at the origin, is the intersection of the two distinct nullclines, the y-axis horizontal and the v-axis vertical. The y-axis was the y nullcline, and the v-axis was the v nullcline. That doesn't always happen. They intersect at the origin. That's not an accident. By definition, the set of equilibrium points is where right-hand sides of the scalar equation say little f and little g are equal to 0. The set of equilibrium points is defined to be all the points in the plane where both f of xy and g of xy equals 0. Or f of yv and g of yv equals 0 for our example. Just one point for our example. We'll see that for linear systems, the set of equilibrium points is either the origin, and that's the typical case, or a line through the origin, or in the most degenerate case, the entire plane. That only happens for one matrix though. That's if capital A is the 0 matrix. 0, 0, 0, 0, all zeros for the entries. Then you get the entire plane to be equilibrium points. Yeah, for non-degenerate linear systems, which is most of them, there will be only one equilibrium point at the origin. In this case, the x nullcline and the y nullcline are distinct lines to the origin in the plane. If the x and y nullclines were the same line through the origin, then that same line would be the set of all the equilibrium points. What are the x and y nullclines for the 0 matrix? Well, they're not lines in that case. Both the x and y nullclines in that case are the entire plane. And that's why the set of all equilibrium points in that case is the entire plane. Hey, linear algebra connection. This is equivalent to saying that the kernel of the corresponding linear transformation, I mean for the matrix that defines our system, is trivial. Just contains the 0 vector. That's the typical non-degenerate case. So that's a connection to linear algebra. And connection to lecture 13b and 14b to come here, this happens exactly when the determinant of the matrix of the linear transformation is non-zero. We're talking 2 by 2 situation here, because we are talking about a phase plane. We could generalize this to higher dimensions, say 3-dimensional phase space, and then the matrix A would be 3 by 3 instead of 2 by 2. But this kind of thing is still going to be true. You're only going to get the origin as the equilibrium point, even in higher dimensions, if and only if the kernel of the corresponding linear transformation is trivial, just the zero vector, if and only if the determinant of that bigger matrix, 3 by 3 or 4 by 4 or 5 by 5, is non-zero. And that is the end of lecture 14a.